In 2012, an annual computer science competition received a submission that achieved something so statistically absurd, the judges genuinely thought there had to be a typo in the code.
Yeah, they thought it was broken.
Right. But it wasn't. A small team of researchers had built a piece of software that didn't just beat the competition. It fundamentally broke the entire paradigm of computer science.
Completely smashed it.
Exactly. It was the kind of, overnight revolution that makes history. But here is the paradox of today's deep dive. The man behind that revolution had spent the previous 30 years being told his life's work was a complete mathematical dead end.
A total waste of time, according to everyone else.
Right. And then, just when his theories conquered the world, he looked at his own creation and warned humanity that we might be making a terrible mistake.
Oh, welcome.
We're so thrilled you're joining us because today we have a story about what happens when you are spectacularly right about something the rest of the world has completely dismissed.
It is, honestly, the ultimate study in scientific conviction. We are talking about a researcher who pursued a discarded, highly unpopular theory through decades of professional exile. And not out of blind ego, but because he recognized a foundational truth about how learning works that the mainstream tech industry simply couldn't accept at the time.
Right. Our mission today is to unpack the fascinating, stubborn, and world-changing journey of Geoffrey Hinton. This is the scientist whose relentless defense of artificial neural networks literally built the foundation for the modern AI boom you and I are living through right now. Okay, let's unpack this because Hinton's starting point is entirely unique. If you look at his intellectual pedigree, he was born into a family tree that is, it's basically royalty in the world of profound abstraction.
Yeah, that context is vital to understand him. Geoffrey Hinton was born in England in 1947, and he descends from a lineage of extreme abstract thinkers. To give you an idea, his great-great-grandfather was George Boole.
Wait, George Boole? Like the guy who invented Boolean algebra?
The very simple.
That is wild. So the logical foundation of true and false, ones and zeros, every piece of silicon on Earth running an if-then statement relies on Boole's math.
Precisely. And it doesn't stop there. His great-uncle was Charles Howard Hinton, who was a mathematician who dedicated his entire life to visualizing four-dimensional space.
Oh, wow. So no pressure at Thanksgiving dinner, right?
Right, exactly. So Geoffrey Hinton inherits this immense capacity to visualize complex, multi-layered systems. But rather than starting in computer science, he took a completely different route. He went to Cambridge to study experimental psychology.
Which makes sense. He wanted to understand the biological mechanisms of human cognition.
Exactly. He wanted to know how the brain actually learns. And what he realized, which, seems obvious to us now, but was radical for computing at the time, is that the human brain does not learn through explicit, hard-coded rules.
Right. A child learning to walk isn't calculating the physics of gravity and, joint angles before taking a step.
No, of course not.
They take a step, they fall, the brain registers the error, and it adjusts the muscle signals slightly for the next attempt. It's this continuous loop of experience, failure, and subtle adjustments.
Yes, and that biological reality was completely at odds with how classical computing operated back then. Traditional computers required rigid, predefined programming. It's very literal.
It's like following a strict baking recipe, right? You measure exactly 1 cup of flour, exactly 1 teaspoon of salt. If you deviate, the cake is ruined.
That's a great way to put it.
But Hinton looked at biological cognition and believed that for a machine to truly exhibit intelligence, it had to learn more like cooking a soup. Tasting it, adding a little salt, tasting it again, adjusting the seasoning over and over through experience.
Exactly. And the theoretical vehicle for this, as you know, was the artificial neural network.
Right. And just to establish the timeline here, Hinton didn't invent the concept of the neural network himself.
No. The foundational idea dates way back to the 1940s. A neurologist named Warren McCulloch and a mathematician named Walter Pitts proposed a theoretical model of how biological neurons might function mathematically.
Okay.
The concept was to build an artificial network of connected nodes, expose that network to data, and let it adjust the strength, or the weights, as they're called, of the connections between those nodes based on its successes and failures.
Which sound incredibly elegant. But looking at the history of the field, the mainstream establishment completely abandoned neural networks by the end of the 1960s. They dropped it cold. Hinton was left working on this nearly alone. So what happened? If mimicking biology makes so much intuitive sense, why did the smartest minds in computer science decide it was a dead end?
What's fascinating here is that the rejection wasn't just a matter of opinion. It was actually a matter of mathematical proof. This leads us to what people call the first AI winter.
The AI winter.
Right. Early researchers quickly realized that simple, single-layer neural networks couldn't solve complex problems. In 1969, Marvin Minsky and Seymour Papert published a landmark book called Perceptrons.
Right, I've heard of this.
Yeah, and they didn't just critique neural networks, they mathematically demonstrated their limitations.
Let's get into the mechanics of that limitation, because it's the exact hurdle Hinton had to jump. Minsky and Papert proved the XOR problem, right?
Exactly. The XOR, or exclusive OR problem. It's a basic logic function where the output is true if one and only one of the inputs is true. Minsky and Papert proved that a simple single-layer network literally cannot draw a mathematical line to separate those inputs.
It just can't do it.
No, it cannot solve nonlinear problems. The only way to solve the XOR problem is to add hidden layers of neurons between the input and the output.
But the catch was, nobody in the 1970s knew how to train a network that had multiple hidden layers.
That was the wall they hit.
They had no mathematical way to tell a neuron buried deep in the middle of the network how much it contributed to an error at the very end of the process. So the whole field basically threw up its hands, declared neural networks a dead end, and cut off all the funding.
That was the consensus. It was over. But Hinton refused to accept it. He believed that if you could figure out how to assign blame for errors deep within a multi-layer network, the system could learn anything.
And that stubborn conviction resulted in a monumental breakthrough in 1986.
Yes.
The backpropagation paper.
Right. He co-authored it with David Rumelhart and Ronald Williams, and it remains one of the most cited papers in all of computer science.
Let's break down backpropagation, because understanding this algorithm is really the key to understanding modern AI.
Backpropagation is essentially the algorithm that solves that multi-layer problem. When a neural network makes a prediction, let's say it's classifying an image, it outputs an answer. If that answer is wrong, backpropagation calculates the exact mathematical gradient of that error. It then propagates that error signal backward through the network, layer by layer, adjusting the weights of every single connection to ensure the network is slightly more accurate the next time.
I always picture it like a game of hot and cold, but played millions of times at lightning speed.
That's a good way to look at it.
You make a guess, and the system tells you, oh, you're getting colder. So you adjust and guess again, and it says, okay, warmer. It's just inching toward the right answer by measuring how wrong it is.
Exactly. In machine learning, that's called gradient descent. Backpropagation calculates the slope of the error, and gradient descent is the network taking a step toward the lowest possible error.
Okay, but wait. If he proved this in 1986, and it was so elegant, why did his career essentially hit a brick wall right afterward?
Well, it's exactly why the second AI winter happened. Because proving backpropagation on paper is very different from executing it efficiently in reality. Throughout the 1990s, the machine learning community shifted almost entirely to a different approach. Support vector machines, or SVMs.
Because SVMs were mathematically guaranteed to work.
Precisely. SVMs utilized convex optimization. So, going back to your hot and